Good evening, friends, and welcome to Sleepy Time Tales, a podcast aimed at helping you to get a good night's sleep. Do you find your mind plagued with the stresses of modern life, especially when the lights are out and you're trying to get a restful night? Does your spinning mind keep you awake? Follow my voice down the path towards a good night's rest. Listen to me tell a story that will keep your mind from wandering to your daytime problems, the ones you can't solve right now and will be easier to solve while rested. Listen to my voice and allow yourself to drift, following the twists and turns of the story, but slowly letting go and drifting into sleep. So what exactly is Sleepy Time Tales? What is it for? What is this strange thing, this strange idea, this podcast that you're supposed to fall asleep to? Lack of sleep is a health crisis in the 21st century, and this is a podcast intended to help those that it can to get a restful night. Do you find yourself lying awake at night, mind spinning and emotions in turmoil with anxieties of 21st century life? Do you wake up in the middle of the night and find yourself not quite able to doze back off at 3 a.m.? I'm here to help. My name is Dave, and I'm your narrator, here to help you into a restful night. Sleepy Time Tales is intended to be used as a distraction to what keeps you awake at night, or sometimes background noise or simply company. As far as I know, there are a couple of different ways to engage with the show. The main idea is that it gives you something to focus on, a story or an event that lets you keep your mind on a specific point, to stop it from spinning out into stress and anxieties, to focus just enough not to resist the embrace of a night's sleep when it comes for you. Or maybe you need something else, maybe you just need some kind of background. Some people like the sound of the ocean, or wind in the trees, or the sound of rain, or maybe just some boring dude droning on. But however you're engaging, however you're using the show, don't force the sleep. Just keep a light mental grip on the thread of the story and allow the need for sleep to come for you naturally. Now, obviously, I'm hoping that you're asleep before I get to the end of the episode. But don't feel pressurized. If this is your first night, this probably actually won't work for you. It'll probably take a solid 3 nights or so to get used to it, to the strangeness of the whole idea, to get used to listening to my voice. Maybe my accent is a little strange to you. Or maybe one episode isn't quite long enough. Of course, there's also the other problem is maybe you don't struggle to go to sleep. Maybe your problem is waking up in the middle of the night. What I do in that case is download a whole bunch of episodes, put them in a playlist, hit play when you go to sleep, and let them go all night. That way, if you wake up, they're still running and you're struggling to get back to sleep, just carry on listening and drift off again. You can even do the same sort of thing if you wake up before the alarm, 60 minutes or even as little as 30 minutes. Carry on listening and just drift off again. And you may wonder what the point of that is. After all, what good is an extra 60 minutes or 30 minutes of sleep? But there is something about that extra relaxation that you get right before the alarm that's satisfying on a whole new, deep level. So relax. If you're new to the show and prone to late nights lying staring at the ceiling, this may seem strange to you. So give it a chance. Because I'm here to work with you, to create a safe space, a cocoon in which you can curl up and allow nature to take its course. So if you're still with me, thank you for staying. If you're already asleep, we'll chat again soon. And of course you aren't hearing me, except maybe in a dream. Before we get on with the show, I'd like to ask for a couple of minutes of your time. First up, I'd like to thank the people who have very generously helped out after my appeal that I've been making in the last couple of weeks. First off is Emily, who signed up to the Patreon. Thank you to Emily for the support. I'm very grateful, and I wish you many well-rested nights. And shout-outs too to the folks who have made very kind contributions via the tip jar. Diane, John, and Sandra have all thrown a little something in the tip jar in the last couple of weeks, and that's very much appreciated. I'm glad to be able to help people to get a good night's sleep, and I'm very happy that folks find it worthwhile to contribute to help me keep the show going. So once again, Emily, Diane, John, and Sandra, thanks so much. And if you too are also finding Sleepy Time Tales useful, if it helps you get a restful night and you would like to help me keep it going out to thousands of insomniacs just like you, and you have the means to help me, please consider supporting on the Patreon at patreon.com/sleepytimetales. This is monthly support that helps me keep the lights on and also gets you bonuses based on your contribution level. And if monthly support is too much to ask for, then, of course, the option is there, like the others have made, to make once-off tips to the tip jar. And as I've mentioned before, I am struggling a bit to keep the show going. It's difficult for me to dedicate the time that it and you listeners deserve, so it needs to justify itself at least a little bit financially. I don't need to earn a living from Sleepy Time Tales, but the current Patreon income and occasional tip doesn't cover the hours I put in. As I've said recently, my audience is 30% bigger than it was a year ago, and the income I'm getting from it is lower, so it's barely covering running costs, never mind the time that I'm putting into it. I'm not planning on shutting down anytime very soon, but if I'm not at least a good way to where I need to be by mid-year, I don't know if I can keep the show going. So I need your help. To emphasize, if you can't afford to make any contributions, please don't feel guilted into it. Times are tough for a lot of people. But if just a few of the thousands of you that listen every week can kick in the price of a cup of coffee or two once a month, I can keep this thing going and maybe even expand. Because I always had quite big plans for Sleepy Time Tales. I'd like to be able to release more episodes and do more exciting things for supporters, so I'd love it if you could help me with that. And now I'm done shaking my tin can and asking for help. Thanks for the patience. Let's get back to the show. We return this week to Astronomy, the Science of the Heavenly Bodies, by David P. Todd. In America, the reflector has always kept at least even pace with the refractor. As early as 1830, Mason and Smith, two students at Yale College, enthused by Denison Olmsted, built a 12-inch speculum with which they made unsurpassed observations of the nebulae. Dr. Henry Draper, returning from a visit to Lord Rosse, began about 1865 the construction of two silver-on-glass reflectors, one of 15-inch diameter, the other of 28 inches, with which he did his important work for many years in photography and spectroscopy, and his mirrors are now the property of Harvard College Observatory. Alvin Clark and Sons have in later years built a 40-inch mirror for the Lowell Observatory in Arizona, and very recently a 6-foot silver-on-glass mirror has been set up in the Dominion of Canada Astrophysical Observatory at Victoria, British Columbia, where it is doing excellent work in the hands of Plaskett, its designer. The huge glass disc for the reflector weighs 2 tons, and it must be cast so that there are no internal strains. Otherwise, it is liable to burst in fragments in the process of grinding. It should be free from air bubbles too, so the glass is cast in one melting, if possible. This disc was made by the Saint-Gobain Plate Glass Company, whose works have been ruthlessly destroyed by the enemy during the war. But fortunately, the great disc had been shipped from Antwerp only a week before the declaration of hostilities. Brashear of Allegheny was entrusted with the optical parts, which occupied many months of critical work. The finished mirror is 73 inches in diameter. Its focal length is 30 feet, and its thickness 12 inches. A central hole 10 inches in diameter makes possible its use as a Gregorian or Cassegrainian type, as well as Newtonian. The mechanical parts of this great telescope are by Warner and Swasey of Cleveland, after the well-known equatorial mounting of the Melbourne reflector by Grubb of Dublin. Friction of the polar and declination axes is reduced by ball bearings. The 66-foot dome has an opening 15 foot wide and extending 6 feet beyond the zenith. All motions of the telescope, dome shutters, and observing platform are under complete control by electric motors. Spectroscopic binaries form one of the special fields of research with this powerful instrument, and many new binaries have already been detected. The great reflectors designed and constructed by Ritchie, formerly of Chicago and now of Pasadena, deserve a special mention. While connected with the Yerkes Observatory, he constructed a 2-foot reflector for that institution, with which he had exceptional success in photography of the stars and nebulae. Later, he built a 5-foot reflector, now at the Carnegie Observatory on Mount Wilson, California, with which the spiral nebulae and many other celestial objects have been especially well photographed. Ritchie's later years have been spent on the construction of an even greater mirror, no less than 100 inches in diameter, which was completed in 1919, and has already yielded photographic results dealt with further on, and far surpassing anything previously obtained. Theoretically, this huge mirror, if its surface were perfectly reflective, so that it would transmit all the rays falling upon it, would gather 160,000 times as much light as the unaided eye alone. Whether a 72-inch refractor, should it ever be constructed, would surpass the 100-inch reflector as an all-round engine for astronomical research, is a question that can only be fully answered by building it and trying the two instruments alongside. Probably 3/4 of all the really great astronomical work in the past has been done by refractors. They are always ready and convenient for use, and the optical surfaces rarely require cleaning and readjustment. With increase of size, however, the secondary spectrum becomes very bothersome in the great lenses, and the larger they are, the more light is lost by absorption, on account of the increasing thickness of the lenses. With the reflector, on the other hand, while there is certainly a greater range of size, the reflective surface retains its high polish only a brief period, so that mere tarnish effectively reduces the aperture, and the great mirror is more or less ineffective in consequence of flexure, uncompensated by the lever system that supports the back of the mirror. Both types of telescopes still have their enthusiastic devotees, and the next great reflector would doubtless be a gratifying success, if mounted in some elevated region of the world, like the Andes of northern Chile, where the air is exceptionally steady, and the sky very clear a large part of the year. The highest magnifying power suitable for work with such a telescope could then be employed, and new discoveries added, as well as important work done in extension of lines already begun on the universe of stars. On the authority of Clarke, even a 6-foot objective would not necessitate a combined thickness of its glasses in excess of 6 inches. Present discs are vastly superior to the early ones in transparency, and there is reason to expect still greater improvement. The engineering troubles incident to execution of the mechanical side of the scheme need not stand in the way. They never have. Indeed, the astronomer has but just begun to invoke the fertile resources of the modern engineer. Not long before his death, the younger Clark had just finished the great lenses of the 40-inch Yerkes telescope, ventured this provision, already in part come true. The new astronomy, as well as the old, demands more power. Problems wait for their solution, and theories to be substantiated or disproved. The horizon of science has been greatly broadened within the last few years. But out upon the borderland I see the glimmer of new lights that await for their interpretation, and the great telescopes of the future must be their interpreters. Practically all the great telescopes of the world have in turn signalized the new accession of power by some significant astronomical discovery. To specify, one of Herschel's reflectors first revealed the planet Uranus, Lord Ross's Leviathan, the spiral nebulae, the 15-inch Cambridge lens, the crepe or dusty ring of Saturn, the 18.5-inch Chicago refractor, the companion of Sirius, the Washington 26-inch telescope, the satellites of Mars, the 30-inch Pulkowa glass, the nebulosities of the Pleiades, and the 36-inch Lick telescope brought to light a fifth satellite of Jupiter. At the time these discoveries were made, each of these great telescopes was the only instrument then in existence with power enough to have made the discovery possible. So we may advance to still further accessions of power with the expectation that greater discoveries will continue to gratify our confidence. Chapter 20. The Story of the Spectroscope. Sir Isaac Newton ought really to have been the inventor of the spectroscope, because he began by analyzing light in the rough with prisms, was very expert in optics, and was certainly enough of a philosopher to have laid the foundations of the science. What Newton did was to admit sunlight into a darkened room through a small round aperture, then pass the rays through a glass prism and receive the band of color on a screen. He noticed the succession of colors correctly: violet, indigo, blue, green, yellow, orange, red. Also that they were not pure colors, but overlapping bands of color. Apparently neither he nor any other experimenter for more than a century went any further, when the next essential step was taken by Wollaston, about 1802 in England. He saw that by receiving the light through a narrow slit instead of a round hole, he got a purer spectrum. Spectrum being the name given to the succession of colors into which the prism splits up or decomposes the original beam of white sunlight. This seemingly insignificant change, a narrow slit replacing the round hole, made Wollaston, and not Newton, the discoverer of the dark lines crossing the spectrum at various irregular intervals. And these singularly neglected lines meant the basis of a new and most important science. Even Wollaston, however, passed them by, and it was Fraunhofer who in 1814 or 1815 first made a chart of them. Consequently, they are known as Fraunhofer lines, or dark absorption lines. Sending the beam of light through a succession of prisms gives greater dispersion and increases the power of the spectroscope. The greater the dispersion, the greater the number of absorption lines, and it is the number and intensity of these lines, with their accurate position throughout the range of the spectrum, which becomes the basis of spectrum analysis. The half-century that saw the invention of the steam engine photography, the railroad, and the telegraph elapsed without any further developments than mere mapping of the fundamental lines A, B, C, D, E, F, G, H of the solar spectrum. The Moon too was examined, and its spectrum was found the same, as was to be expected from sunlight simply reflected. Sir John Herschel and other experimenters came near guessing the significance of the dark lines. But the problem of unraveling their mystery was finally solved by Bunsen and Kirchhoff, who ascertained that an incandescent gas emits rays of exactly the same degree of refrangibility, which it absorbs when white light is passed through it. This great discovery was at once received as the secure basis of spectrum analysis, and Kirchhoff in 1858 put in compact and comprehensive form the three following principles underlying the theory of the science. Solid and liquid bodies, also gases under high pressure, give when incandescent a continuous spectrum, that is, one with a mere succession of colors and neither bright nor dark lines. Gases under low pressure give a discontinuous spectrum, crossed by bright lines whose number and position in the spectrum differ according to the substances vaporized. When white light passes through a gas, this medium absorbs or quenches rays of identical wavelength, with those composing its own bright line spectrum. Clearly, then, it makes no difference where the light originates, whether it comes from sun or star. Only it must be bright enough that we can analyze it with a spectroscope. But our analysis of sun and star could not proceed until the chemist had vaporized in the laboratory all the elements and charted their spectra with accuracy. When this had been done, every substance became at once recognizable by the number and position of its lines, with practical certainty. How then can we be sure of the chemical and physical composition of sun and stars? Only by detailed and critical comparison of their spectra with the laboratory spectra of elements which chemical and physical research have supplied. As in the sun, so in the stars, each of which is encircled by a gaseous absorptive layer or atmosphere. The light rays from the self-luminous inner sphere must pass through this reversing layer, which absorbs light of exactly the same wavelength as the lines that make up its own bright line spectrum. Whatever substances are here found in gaseous condition, the same will be evident by dark lines on the spectrum of sun or star, and the position of these dark lines will show, by coincidence with the position of the laboratory bright lines, all the substances that are vaporized in the atmospheres of the self-luminous bodies of the sky. Here then originated the science of the new astronomy. The old astronomy had concerned itself mainly with positions of the heavenly bodies, where they are. The new astronomy deals with their chemical composition and physical constitution, and what they are. Between 1865 and 1875, the fundamental application of the basic principles was well advanced by the researches of Sir William Huggins in England, of Father Angelo Secchi in Rome, of Jules Janssen in Paris, and of Dr. Henry Draper in New York. In analyzing the spectrum of the sun, many thousands of dark absorption lines are found, and their coincidences with the bright lines of terrestrial elements show that iron, for instance, is most prominently identified, with rather more than 2,000 coincidences of bright and dark lines. Calcium too is indicated by peculiar intensity of its lines, as well as their great number. Next in order are hydrogen, nickel, and sodium. By prolonged and minute comparison of the solar spectrum with spectra of terrestrial elements, something like 40 elemental substances are now known to exist in the Sun. Rowland's splendid photographs of the solar system have contributed most effectively. About half of these elements, though not in order of certainty, are aluminium, cadmium, calcium, carbon, chromium, cobalt, copper, hydrogen, iron, magnesium, manganese, nickel, scandium, silicon, silver, sodium, titanium, vanadium, yttrium, zinc, and zirconium. Oxygen too is pretty surely indicated, but certain elements abundant on Earth, as nitrogen and chlorine, together with gold, mercury, phosphorus, and sulfur, are not found in the Sun. The two brilliant red stars, Aldebaran in Taurus and Betelgeuse in Orion, were the first stars whose chemical constitution was revealed to the eye of man. And Sir William Huggins of London was the astronomer who achieved this epoch-making result. Father Secchi of the Vatican Observatory proceeded at once with a visual examination of the spectra of hundreds of the brighter stars. And he was the first to provide a classification of stellar spectra. There were 4 types. Secchi's type 1 is characterized chiefly by the breadth and intensity of dark hydrogen lines, together with a faintness or entire absence of metallic lines. These are bluish or white stars, and they are very abundant, nearly half of all the stars. Vega, Altair, and numerous other bright stars belong to this type, and especially Sirius, which gives to the type the name Sirians. Type 2 is characterized by a multitude of fine dark metallic lines, closely resembling the lines of the solar spectrum. These stars are somewhat yellowish in tinge like the Sun, and from this similarity of spectra they are called solars. Arcturus and Capella are solars, and on the whole the solars are rather less numerous than the Sirians. Stars nearest to the solar system are mostly of this type, and according to Kapteyn of Groningen, the absolute luminous power of the first type of stars exceeds that of the second type of stars 7-fold. Secchi's type 3 is characterized by many dark bands, well defined on a side towards the blue end of the spectrum, but shading off toward the red. A colonnaded spectrum, as Miss Clark aptly terms it. Alpha Herculis, Antares, and Mira, together with orange and reddish stars and most of the variable stars, belong in type 3. Type 4 is also characterized by dark bands, often called flutings, similar to those of type 3, but reversed as to shading. That is well defined on the side toward the red, but fading out towards the blue. Their atmospheres contain carbon, but they are not abundant, besides being faint and nearly all blood red in tint. Following up the brilliant researches of Draper, who in 1872 obtained the first successful photograph of a star's spectrum, that of Vega, Pickering of Harvard supplemented Secchi's classification by type 5, a spectrum characterized by bright lines. They too are not abundant, and are all found near the middle of the galaxy. These are usually known as Wolf-Rayet stars, from the 2 Paris astronomers who first investigated their spectra. Type 5 stars are a class of objects seemingly apart from the rest of the stellar universe. and many of the planetary nebula yield the same sort of spectrum. The late Mrs. Anna Palmer Draper, widow of Dr. Henry Draper, established the Henry Draper Memorial at Harvard. An investigation of the photographic spectra of all the brightest stars of the entire heavens has been prosecuted on a comprehensive scale. Those of the northern hemisphere at Cambridge and of the southern at Arequipa, Peru. These researches have led to a broad reclassification of the stars into 8 distinct groups, a work of exceptional magnitude, begun by the late Mrs. Fleming and recently completed by Miss Annie Cannon, who classified the photographic spectra of more than 230,000 stars on the new system as follows. The letters O, B, A, F, G, K, M, N represent a continuous graduation in the supposed order of stellar evolution, and further subdivision is indicated by tenths. G5K meaning a type halfway between G and K, and usually written G5 simply. B2 would indicate a type between B and A, but closer to B than A, and so on. On this system, the spectrum of a star in the earliest stages of its evolution is made up of diffuse bright bands on a faint continuous background. As these bands become fewer and narrower, very faint absorption lines begin to appear. First the helium lines, followed by several series of hydrogen lines. On the disappearance of the bright bands, the spectrum becomes wholly absorbed of bands and lines. Then comes a very great increase in intensity of the true hydrogen spectrum, with wide and much diffused lines, and few, if any, other lines. Then the H and K calcium lines and other lines peculiar to the Sun become more and more intense. Then the hydrogen lines go through their long decline. The calcium spectrum becomes intense, and later the spectrum becomes quite like that of the Sun, with a great wealth of lines. Following this stage, the spectrum shortens from the ultraviolet. The hydrogen lines fade out still further, and bands due to metallic compounds make their appearance. The entire spectrum finally resembling that of sunspots. To designate these rather more categorically, Type O, bright bands on a faint continuous background with 5 subdivisions, OA, OB, OC, OD, OE, according to the varying width and intensity of the bands. Type B, the Orion type or helium type, with additional lines of origin unknown as yet, but without any of the bright bands of type O. Type A, the Sirian type, the regular Balmer series of hydrogen lines being very intense, with a few other lines not conspicuously marked. The calcium type, hydrogen lines less strongly marked, but with narrow calcium lines, H and K, very intense. Type G, the solar type, with multitudes of metallic lines. Type K, in some respects similar to G, but with the hydrogen lines fading out, and the metallic lines relatively more prominent. Type M, spectrum with peculiar flutings due to titanium oxide, with subdivisions MA and MB, and the variable stars of long period, with a few bright hydrogen lines additional, in a separate class, MD. Type N, simpler to M, in that both are pronouncedly reddish, but with characteristic flutings, probably indicating carbon compounds. The Draper classification, being based on photographic spectra, and the original Secchi classification being visual, the relation of the two systems is approximately as follows. Secchi Type 1 includes Draper B and A. Type 2 includes Draper F, G, and K. Type 3 includes Draper M. Type 4 includes Draper N. Pickering's marked success in organization and execution of this great program was due to his adoption of the slitless spectroscope, which made it possible to photograph stellar spectra in vast numbers on a single plate. The first observers of stellar spectra placed the spectroscope beyond the focus of the telescope with which it was used, thereby limiting the examination to but one star at a time. In the slitless spectroscope, a large prism is mounted in front of the objective of short focus, so that the star's rays pass through it first, and then are brought to the same focus on the photographic plate for all stars within the field of view, sometimes many thousand in number. This arrangement provides great advantages in the comparison and classification of stellar spectra. When spectroscopic methods were first introduced into astronomy, there was no expectation that the field of the old, or so-called exact astronomy, would be invaded. Physicists were sometimes jocularly greeted among astronomers as ribbon men, and no one even dreamed that their researches were one day to advance to equal recognition, with results derived from micrometer, meridian circle, and heliometer. The first step in this direction was taken in 1868 by Sir William Huggins of London, who noticed small displacements in the lines of spectra of very bright stars. In fact, the whole spectrum appeared to be shifted. In the case of Sirius, it was shifted toward the red, while the whole spectrum of Arcturus was shifted by 3 times this amount towards the violet end of the spectrum. The reason was not difficult to assign. As early as 1842, Doppler had enunciated the principle that when we are approaching or approached by a body which is emitting regular vibrations, then the number of waves we receive in a second is increased, and the wavelength correspondingly diminished. And just the reverse of this occurs when the distance of the vibrating body is increasing. It is the same with light as with sound, and everyone has noticed how the pitch of a locomotive whistle rises as it passes, and falls as suddenly on retreating from us. So Huggins drew the immediate inference that the distance between the Earth and Sirius was increasing at the rate of nearly 20 miles per second, while Arcturus was nearing us with a velocity of 60 miles per second. Those pioneer observations of motions in the line of sight, or radial velocities as they are now called, led directly to the acceptance of the high value of spectroscopic work as an adjunct of exact astronomy and stellar research. Nor has it been found wanting in application to a great variety of exact problems in the solar system, which have been wholly impossible to solve without it. Foremost is the sun, of course, because of the overplus of light. Young early measured the displacement of lines in the spectra of the prominences, and found velocities sometimes exceeding 250 miles per second. Many astronomers, Donner among them, investigated the rotation of the sun by the spectroscopic method. The sun's east limb is coming towards us, while the west is going from us. And by measuring the sum of the displacements, the rate of rotation has been calculated. Not only at the sun's equator, but at many solar latitudes also, both north and south. As was to be expected, these results agree well with the sun's rotation, as found by the transits of sunspots in the lower latitudes where they make their appearance. Belopolsky has applied the same method to the rotation of the planet Venus and Keeler by measuring the displacement of lines in the spectrum of Saturn on opposite sides of the ring, provided a brilliant observational proof of the physical constitution of the rings, because he showed that the inner ring traveled more swiftly than the outer one, thus demonstrating that the ring could not be solid, but must be composed of multitudes of small particles traveling around the ball of Saturn, much as if they were satellites. Indeed, Keeler ascertained the velocity of their orbital motion, and found that in each case it agreed exactly with that required by the Keplerian law. Even the fulmy corona of the Sun was investigated in similar fashion by Deslandres at the total eclipse of 1893, and he found that it rotates bodily with the Sun. But the complete vindication of the spectroscopic method as an adjunct of the old astronomy came with its application to measurement of the distance of the Sun. The method is very interesting and was first suggested by Campbell in 1892. Spectrum line measurements have become very accurate with the introduction of dry plate photography, and ecliptic stars were photographed toward and from which the Earth is traveling by its orbital motion around the Sun. By accurate measurement of these displacements, the orbital velocity of the Earth is calculated. And as we know the exact length of the year, or a complete period, the length of the orbit itself in miles becomes known. And thus, by simple mensuration, the length of the radius of the orbit, which is the distance of the Sun. And I think I'm going to leave it there. As always, you can pick up where we've left off on Project Gutenberg at the link in the show notes. Thanks again for joining me on this episode of Sleepy Time Tales, the podcast designed around a bedtime story to help you to get a restful night. New episodes will be released every Sunday night to give you something fresh to help you rest in a new week. But make sure to follow or subscribe in whatever service you use, so that you can get your new episodes whenever they come out. Good night, and sweet dreams.